Hey there guys. So today I want to talk to you about one of the most important topics in statistics. And it's one with you've had a background in statistics a little bit before taking this course, and you've probably done some basic statistics and you've seen this term a lot. Basically what I'm going to talk about today is the notion of p-value. So you already know, since you've done some statistics, that p-value comes up a lot. And in fact, virtually every statistic that we will calculate, I guess not everything, I can think of one or two that we might calculate that won't have a p-value associated with them. But for example, when we do a t-test, we'll get a t statistic. When we do ANOVAs, we'll get an f statistic. When doing a Shapiro-Wilk W test, we'll get a W statistic, and so on. We'll get chi-squares, etc. So we get a number of different kinds of statistics, and the values themselves of W, F, chi-squared, and T are the statistics. So if you didn't know what a statistic was, it's those indices that we get, that we calculate from data somehow, some way. And so with every statistic, or almost every statistic, we will get an associated p-value. And this associated p-value is giving us a context for interpreting that statistic. And so we really need to understand at a fundamental level what that p-value is actually giving us. Okay, so first of all, p-values in terms of just range can range anywhere between 0. They can't actually be a 0. I guess they have to be greater than 0. And they can be up to 1. So it's a probability, first of all. And the important thing is to understand it's a probability of what. And in that context, then, I think it's interesting to think about how JMP reports p-values and other statistics programs too. So when it gives you a t statistic, for example, you might get a t value of 3.218, and you then might get a probability associated with that t value. And so the t value has a p-value associated with it. I don't know, let me give that an example. So I'm just making this up, don't quote me on this, but let's say the p-value is 0.024. So this p-value does meet the criteria of being between 0 and 1, and it's a probability. But we've got to understand what this probability means. So first of all, it's not given in a percent, it's a probability between 0 and 1. So this is a 2.4% probability of something. Okay, so we can translate that just by multiplying by 100 into percent probability. But the basic p-values are typically not reported that way. But that might help you interpret some p-values. Okay, so what is this p-value actually giving you? So the way JMP reports it is it says it gives the p-value as probability of a greater t. And it will, list that as a heading for a column and put 0.024 under that associated with this particular t-value. So it will have a part of the table, which is the t, 3.218, let's say, and then it will have an associated probability of 0.024 associated with that. And the way it gives it is as this, the probability greater t. And the way you read that is the probability of obtaining a greater t than the one we obtained. So it's actually referring to this particular t value. All right, so let's think about what that means. So probability of a greater t. And by the way, for the t-test, it will often be probability of a greater absolute value of t, and that will be the one we look at for a two-tailed test. I'll go into the differences between two-tailed and one-tailed tests, but since most of you have had the t-test, you already kind of know. So the two-tailed t-test, and then this might be if we had a one-tailed test. And by the way, this could be written either probability of a lesser t or probability of a greater t, depending upon what our hypothesis was about the which side of the mean it was found on, our particular sample mean was found on. Okay, so anyway, going back to this one, which we'll take as the two-tailed test, and we'll concentrate on that. So how do we read this? We read it as the probability of obtaining a t larger than the one we obtained. But that probability is with respect to a particular hypothesis. And it is with respect to the null hypothesis. If the null hypothesis sorry, here I'm having trouble with my pen. If the null hypothesis is true. All right, now this is where it gets a little bit complicated, and you have to sort of think about this. So what is our null hypothesis typically? Our null hypothesis in the case of a t-test is that if we're comparing, as we will with our first test, a sample mean to a hypothesized mean, our null hypothesis is that the sample mean equals the hypothesized mean. Okay? Or if we were talking about two populations, it is that the the mean of population A equals the mean of population B. Really, we should say the mean of the population from which sample A was drawn is equal to the mean of the population from which sample B was drawn. Right? It's not really that our two samples had the same mean. It's that they were drawn from parametric populations behind our sample that had actually the same parametric means. Okay, so that's the null hypothesis, and it's important then to think about that in the process of interpreting this probability. So it's the probability of obtaining a t that large when in fact the null hypothesis is true. Okay, so let's revisit then our p equals 0.024 that I talked about a moment ago. So what does this mean? This means that we have a 2.4% chance of getting a t that large or larger when mu A for our sample equals our hypothesized mean. Okay, so that's what we're going to do for our first t-test that we do. Okay, so there's a 2.4% chance. That's a small chance, and therefore typically what we would say is that's a very low chance that actually our sample mean is drawn from a population with a true mean that is the same. And so we reject that null hypothesis in this case. And the criterion for rejecting it is something we'll talk about actually in a separate video. Right now, we're just talking about what this probability of 0.024 means. And it means we have a 2.4% chance of getting a t that larger when in fact the population is drawn from a parametric population that has the same mean as the hypothesized mean. Okay, so that's all it means. Another way we can interpret it is that the p-value is the probability of being incorrect in rejecting the null hypothesis. Right? Because if that's the probability of obtaining a t that large when in fact the null hypothesis is true, we would be incorrect that amount of time too in rejecting it. And so, for example, typically, if you get a pretty large p-value, let's say you get a p-value of 0.361 associated with some t value. Let's imagine the t, I'm just making these numbers up. Let's say t was 0.824, okay? And our associated p-value with that was 0.361. That would be a 36.1% chance of being incorrect if we rejected the null. And so what would we do? And so we don't. We don't reject the null. Okay, but making that decision about rejecting or not rejecting the null is the subject of our next talk. So I'll get there in a moment, and what I want to do is direct you to our video on alpha. Okay, alpha, and so you'll look at that to understand our decision making about what p means. Beyond that, in terms of how we interpret statistical significance, but I do want to kind of say, a given p-value, you should not call that the significance. Okay, it's not really a good name for it. I mean, it is the probability of getting a T or an F or whatever, that larger. By the way, it's not always larger. It could be smaller. It depends how the probability is written. But just referring it to as significance, it's too much of a shorthand. Okay, it doesn't really explain what that is. And as a sophisticated statistical user, you should now be able to, when pressed, say more precisely what that probability actually means. Okay. And the other thing I'd like to say just about p-values generally is we often think of low p equals a good thing, and a high p equals a bad thing. And I kind of point to this t-shirt over here. My p-value is smaller than your p-value. As an example of this, I found this on the internet. So you can buy this shirt if you wish, but the implication is that a small p-value is actually good and a high p-value is bad. And in statistics, we are doing a scientific objective analysis of our data, and this is not a good way to think about p-values. Think of p-values as they are what they are. They are probabilities of getting that particular t-value by chance, when in fact the null hypothesis is true. Okay, so that's all it is. We don't wish for something in terms of a particular p-value. We don't reanalyze the data till we get what we want. We do it objectively, and we do it using basic scientific principles, and whatever happens, whatever p-value we get, is what we need to accept. If we've done the appropriate test, if our data are input correctly, etc., then when we get a p-value out, we need to live with it, report it, and it is what it is. Okay, so the p-value is something that gets reported in results sections. The interpretation of the p-values, that comes later. I mean, we make qualitative judgments about those p-values afterwards, and as a separate process from the simple reporting of this probability, because the probability is what it is. It is not good, it's not bad. You shouldn't brag about it being smaller than someone else's p-value, because the point is not trying to prove a significant p-value. Okay, you've designed an experiment that's designed to test the null hypothesis. If you've designed it well, then you get a p-value that's telling you something scientifically important about your data, and that's the important thing, whether it's significant, i.e. different from some threshold we've set, or not. Okay, so that's very important. We report p-values, and by the way, that philosophy is incorporated in much of science now, where we report exact p-values, not as thresholds. And again, I will talk about that when we talk about alpha in the next video. But to keep this short, I'll leave it right there. But we report exact p-values because they are, in fact, a continuum. And if we have a p of 0.049, it doesn't mean the same thing as a p of 0.0001, for example, 0101, let's say. All right, so in the long distant past, someone might have put these in the same category of p less than 0.05, but now we report exact p-values because these have quite different meanings. One of them is about 5 times larger than the other. Okay, all right, folks, that's it for p-value. I hope you never again can't really answer when pressed the question, what is p-value? By the way, for graduate students watching this, this comes up on prelims exams a lot. And if you really can't say what a p-value is, you're kind of in trouble.